Hello everyone. In this section, let's look at the reactivities of aldehydes and ketones. Okay. Aldehydes and ketones, they are considered as electrophiles. Electrophiles are electron deficient species, or you can say E plus electrophile, meaning it doesn't have enough electrons, electron deficient. So electrophiles normally react with nucleophiles. Nucleophiles are electron rich species like this. If you look at the carbonyl compound resonance structure, if you draw the resonance for this one, we can draw carbon, alkyl group or hydrogen, oxygen. You can draw a resonance structure. The pi bond will open up, oxygen will be negative and carbon would be positive. So this carbon, the carbonyl carbon carries a positive charge. We know that both are possible resonance structures, though the neutral one, which is this one, takes the more prominent species in the resonance, but the plus minus separated ion also a resonance product, resonance compound. Okay, so carbon is more electropositive. Now normally if you can increase the partial positive charge, making it a more electrophile, but if you decrease the partial positive charge, it would become less electrophilic, right? So if you have a positive charge, how can you stabilize a positive charge? Remember the carbocations that we learned in organic 1. We said the tertiary carbocations are more stable. Why? Because they have alkyl group, 3 groups, and through the hyperconjugation you can donate electrons towards the carbon. Carbon positive means it's electron deficient. When the alkyl groups donate carbons, what happens? So then the carbon positivity decreases, it gets some electrons. So then you tell me which one, if you compare aldehyde and a ketone. So let's say this is ketone and this is an aldehyde. Which one do you think would be more reactive towards a nucleophile? The carbon that has more positive character or a carbon that has a less positive character? So let me take a different color. So these two, there are 2 carbons that can donate electrons towards hyperconjugation and decrease the positive charge on carbon, whereas this one has only 1 alkyl group. So the aldehyde can keep that positive charge more than the ketone. Okay, so normally because of that, aldehydes are more reactive compared to the ketones. Okay, so this is how nucleophile react with a carbonyl group. So the nucleophile here carrying electrons or a negative charge attacks the carbon, because you saw that the carbon going to be partially positive and oxygen negative. Once the nucleophile attach, carbon already has 1, 2, 3, 4 bonds. So then one of the bonds needed to be broken. Okay, so there are 4 bonds, 1, 2, 3, 4. Which one is going to break? So these are sigma bonds. What do we have in a double bond? We have 1 sigma and 1 pi. It's always easier to break the pi bonds than the sigma bond. So it's always the pi bond, the double bond, that gets broken. And in the double bond also, it's the pi bond that breaks up and give 2 electrons to the oxygen. So then you will have 4 bonds in your intermediate. But this is how normally a carbonyl group react with a nucleophile. The partial positive charge on the carbonyl carbon causes it to be an electrophile, so it reacts with nucleophiles. So you will see this pattern very, very often. Aldehydes are more reactive than ketones for the reason that I explained in the previous slide. And even in the aldehydes, formaldehyde is the most reactive because it only has hydrogens. There are no electron donating alkyl groups. And then the aldehyde, and then between aldehyde and ketone would be least reactive compared to the aldehyde. Aldehyde has a greater partial positive charge for the same reason I explained on its carbonyl carbon than as a ketone. The carbonyl carbon of an aldehyde is more accessible to the nucleophile. Another reason why aldehydes are more reactive, it is less crowded at the carbonyl carbon. You can see in a ketone there are two alkyl groups. In aldehyde you have one alkyl group and hydrogen. So the incoming nucleophile can reach the aldehyde more easily. It's more easily accessible, less steric crowding. That's another reason why aldehydes are more reactive compared to the ketones. So the bond angle, so this is trigonal planar, bond angle would be 120. Ketones have greater steric crowding in their transition states. So their transition states are less stable than those of aldehydes. So most reactive ketone. So there are two methyl groups. But the more substituents on any of these carbons will make ketone less reactive. So this carbon has two methyl groups and these both carbons have methyl group. So this would become least reactive. And with the other carbonyl groups, we have this order of reactivity. They are moderately reactive carbonyl compounds. We just compared between the aldehydes and the ketones, but there are some excuse me, other carbonyl groups containing compounds like ester, carboxylic acid, amides, carboxylate ion. They are going to be less reactive compared to ketones and aldehydes, and there are two other compounds going to be more reactive than aldehydes. That's going to be acid anhydride and acyl halide. This is the most reactive one. Okay, aldehydes and ketones are less reactive than acyl halides and acid anhydrides. Aldehydes and ketones more reactive than esters, carboxylic acids, amides and carboxylate ions. These are the things that can happen when a nucleophile attacks a carbonyl group. So these are some general examples, but we will look at these each kind when we are looking at the specific reactions. Aldehydes and ketones react differently than carboxylic acid derivatives. Nucleophilic acyl substitution. Substitution, we know what substitution means, meaning that you're going to be substituting a group. The number of groups remains the same then, since you're going to substitute. That occurs when Y is a group, Y is a leaving group that can be replaced by another group. If this Y group that is attached to the carbonyl group can be replaced by another group like Z, so then you can have a substituted product. Instead of Y, now you have Z, but it's going to go through this four-membered carbon tetrahedral intermediate. First, the Z would add nucleophile, always adds to the carbon. Okay, eventually the carbon and Y bond is going to break, but before it breaks, it first breaks the double bond, pi bond here, and you're going to have this tetrahedral intermediate, okay, with the four bonds, and then it reforms the pi bond and leave Y. We'll look at these mechanisms later on in detail. Okay, so product of nucleophilic acyl substitution. Z has substituted for Y. So this is one kind of a reaction that the carbonyl functional groups undergo, especially your aldehyde and ketone, since we are talking about that functional groups here. And then you have nucleophilic addition. You see the difference. This is nucleophilic substitution. Now the nucleophilic addition occurs when Y is a group that cannot be replaced by another group. Z added here to the carbonyl group. Let's say you have two alkyl groups, and then again you form the four-membered intermediate. Pi bond breaks, Z is added. The reaction is irreversible. Once the Z is being formed, it cannot go back. You cannot remove easily Z. Z is too basic to be eliminated, like your hydroxide. Remember, it's difficult to eliminate, but if you make it a water molecule, it's possible. So if it cannot be removed again, then the product is nucleophilic addition product. Okay? So these two can undergo with carbonyl groups and a nucleophile. That one of the products would be nucleophilic substitution, the other one would be nucleophilic addition. And then some additions of nucleophiles to aldehyde and ketones lead to an addition-elimination product. Okay, so addition-elimination. Here's another way that these carbonyl groups undergo reactions. Let's say from the previous one, nucleophilic addition, you have this compound here. Okay. Then, so this is the product of the nucleophilic addition, and the nucleophile has a lone pair. Nucleophile has this also could be another alcohol group like OH. And then you put water, or this could be like an amine group in nitrogen with a lone pair. You add water, acidic medium, hydronium ion is acidic water. You add, so then the OH can be protonated to give you a protonated alcohol. So with the lone pair can act as a nucleophile and then gives its electrons as a base, I would say. Lone pair gives its electrons to form the pi bond between the carbon and the Z, and then it leaves this water molecule. Now again it formed another product, that is addition, and then you did elimination. What is eliminated? So this is a product of nucleophilic addition elimination. So we will see these patterns when we are looking at what are the kind of reactions that these carbonyl groups undergo. Nucleophilic addition elimination occurs when the nucleophile has a lone pair, like a nitrogen group or oxygen group, has a lone pair on the attacking atom. Water rather than a group attached to the carbonyl group is eliminated. So water is eliminated. Water is part of the carbonyl group, but the groups attached to the carbonyl group is alkyl and this is the two different alkyl groups. They normally do not break the sigma bonds because it's hard to break carbon-carbon bond, but carbon-oxygen bond more polar, and you are creating a neutral molecule, so that leaving a neutral water molecule and breaking the carbon-oxygen polar bond is much more easier than breaking a carbon-carbon bond. Okay, we need more harsh reactions to break a carbon-carbon bond. So that's what it says, water rather than a group attached to the carbonyl group is eliminated. Okay. Now let's see how the carbonyl groups react with Grignard reagents. Remember, we learned about the Grignard reagent in the previous section, chapter 11. We talk about that it can form new carbon-carbon bonds. Okay, and let's see how this is going to react. Formation of a new carbon-carbon bond using a Grignard reagent. First thing is to make the Grignard reagent. You start with the alkyl halide. You mix it with magnesium and diethyl ether. Ether is a solvent. Magnesium is needed to make the Grignard reagent. So the magnesium gonna go insert between the carbon and the bromine. So you're gonna make ethyl magnesium bromide. And we learned that magnesium is positive, partial positive, a metal, and then carbon would be partially negative. Or can consider carbon is, the bond is being broken between the carbon and the magnesium. Magnesium is positive and carbon is negative. So it can act as a carb anion, so which is a nucleophile. So alkyl magnesium bromide. Okay, so it reacts. The bond between the alkyl group and the magnesium breaks, and the carrying the 2 electron goes and attack this carbon. I'm redrawing the same thing because some students like to see it like that, how it happens, even though it's drawn there. And then the carbon-oxygen bond is going to break, pi bond. Okay, always when you are adding a nucleophile to the carbon, you cannot stop the arrow right there. You have to further go ahead and break that pi bond between the carbon and oxygen, just like shown in this red arrow. Then what would happen? So the two electrons on the pi bond now end up on oxygen, so oxygen will be negatively charged. So the two electrons here went to form the bond between the carbon and the alkyl group. Now new bond is being formed. Magnesium is losing these two electrons, so the magnesium would be positively charged. So in the intermediate, oxygen is negatively charged, magnesium is positively charged. So they balance their charges. So this magnesium will stay somewhere closer to oxide, alkoxide, O minus MgBr, kind of to make it stabilize. Okay. And once you form this product, you add acidic water. You can add hydrochloric acid or sulfuric acid. Then this alkoxide ion grabs a proton from the hydronium ion. So hydronium ion is this, oxygen with a positive charge. So this guy goes and grab a hydrogen, gives his electrons to the oxygen. So then it would generate plus water. So this O minus will become OH. O minus will become OH. Now you have created an alcohol. Now what did we learn here? If you started Grignard reagent with aldehyde or a ketone, alkyl group on the Grignard reagent R prime will add on to the carbon of the carbonyl group in the aldehyde or the ketone, and you will get an alcohol, OH. Now this is not a substitution, nucleophilic substitution reaction. This can be considered as a nucleophilic addition reaction because we added an alkyl group. Okay. Reactions of aldehydes and ketones with Grignard reagents. So here again, so this is the Grignard reagent. You have an alkyl group, ethyl group. This is the formaldehyde. So we should be able to see and say what is the product that we're going to get. Alkyl group will add to the carbon, and this would end up being alcohol. That is the end product. So carbon, magnesium, carbon is negatively charged. Go and attack the carbonyl carbon, pi bond opens up. You have this intermediate CH3CH2. To this carbon added this formaldehyde carbon with two hydrogens, oxygen, and then the counter ion magnesium bromide. In the second step, when you add acidic water, this would become alcohol. Okay, so formaldehyde will give you 1-propanol, a primary alcohol. If you want to get a different alcohol, you can change the alkyl group of the magnesium bromide of the Grignard reagent. Okay. Now in this one, you start with propanol. 1, 2, 3. You're adding methyl magnesium bromide. So what should be the end product? So the methyl group will end up on the carbon, and this would become alcohol. So the aldehyde will become a secondary alcohol, 2-butanol, a secondary alcohol, because you add a methyl group on the carbon and then this became OH. Okay, same mechanism. And then 2-pentanone, this is a ketone. You add this group, ethyl magnesium bromide. This ethyl group adds on to the carbon, carbonyl carbon, and this would become OH. After you add hydronium ion, acidic medium, it becomes a tertiary alcohol. Now this happens in 2 steps. Adding the Grignard reagent to the carbonyl compound, we have to do it without having any acidic water in the reaction mixture. You let it stir according to the recipe, how long it needs to be done. And then once the Grignard reagent is being formed, then in the second step you add hydronium or the acidic acid. It could be sulfuric acid, it could be hydrochloric acid. You can add that. You don't add Grignard reagent and the acid together. Otherwise, this can destroy by taking a hydrogen from the hydronium ion. Okay. Grignard reagent reacts with carbon dioxide to form carboxylic acid. Now, carbon dioxide also has a carbonyl group and another carbonyl group, two carbonyl groups. So here you have a propyl magnesium bromide, same mechanism. Carbon attacks the carbonyl carbon, opens one of the carbon oxygen bonds. It could be the other one too. And then this propyl group attached to the carbon, and one side we still have the carbonyl group, and then the oxygen will carry magnesium bromide. Second step, you add hydronium ion or your acid, and then it became an acid, which is butanoic acid. Okay. Carboxylic acid has one more carbon than the Grignard reagent. So if you want to make an acid with carbon dioxide, depending on the number of carbons you want, you can choose the type of Grignard reagent you want. Okay. Examples of reactions with Grignard reagents. Same thing that we have seen before, but we have more examples here. So this is 3-pentanone. Again, what is the product going to be? Always remember the methyl magnesium bromide, the alkyl group coming from the magnesium bromide Grignard reagents attached to the carbonyl carbon, and this would become alcohol. OH and CH3, EC, 3-methyl-3-pentanol. For this one, benzene magnesium, phenyl magnesium bromide, not benzyl, phenyl magnesium bromide. Phenyl group will attach to the carbon and this become OH. 1 phenyl, 1 butanol. Numbers above and below arrows. You see number 1, 2. First step, adding methyl magnesium bromide. In the second step, adding water, acidic water. Numbers above and below arrows mean that the acid is not added until the Grignard reagent has reacted with the carbonyl compound. When a reaction, okay, so remember I talked about this earlier, because Grignard reagent, if you add the acid and this together, since this is very basic, it can react with the hydronium ion and become methane. So this would not be available to react with your carbonyl compound. So this has to be done in 2 steps. When a reaction creates an asymmetric center from a compound without an asymmetric center, the product is a racemic mixture. Like for the second example, there is no asymmetric carbon here. But this one we do, a chiral center. This carbon has 4 different groups attached to it. OH group, propyl group, hydrogen, and a phenyl group. So this would come as a racemic mixture, meaning you will have 50-50 mixture of R and S enantiomers. Okay, so that's how aldehydes and ketones react with Grignard reagents. Now this is the way a Grignard reagent reacts with an ester. So ester, this is an example of an ester. It has one side of the carbonyl group, you have alkyl group, and on the other side of the carbonyl group, you have an alkoxy group, oxygen and another alkyl group. Now to this one, since it also has a carbonyl group, it can also react with Grignard reagent. Now you know what's going to happen. Methyl group will go to this carbon and this would become OH. Okay. And okay, it's gonna go all the way. Wait a minute. So once you form that, it's going to form a ketone by eliminating this methoxy group. Okay, so this is a ketone. In the first step, you are making a ketone. But after you eliminate this product, I'll show you with the mechanism below. And then since you have created another ketone here, Now the ketone can undergo another nucleophilic addition with another Grignard reagent. So the end product would be, if you start with an ester, two alkyl groups from the Grignard reagent would end up adding to the carbonyl group. So methyl. So this can now again attack the carbonyl carbon, and then you have two methyl groups. And then when you do the acid workup, this would become alcohol. Okay, so basically if you start with an ester, you would end up getting a tertiary alcohol. Okay, and this is how the mechanism occurs. Just like the Grignard reagent would react with the carbonyl group, carbon magnesium bond, nucleophilic, goes and attack the carbon, pi bond opens up, and you create this intermediate. A group is eliminated from the tetrahedral intermediate. Now you have 1, 2, 3, 4 groups. From here, methoxide can be released by reforming the carbonyl group. You are breaking a carbon-oxygen bond. Remember, carbon-oxygen bond is more polar. So it's easy for carbon-oxygen bond to break rather than carbon-carbon bonds break. So the bond that is going to break is the carbon-oxygen bond, methoxy bond. So this reforms the carbonyl group, pi bond, and leaves the methoxy group, methoxide, okay, as a methoxide anion. Now the methoxide anion would be stabilized with the magnesium bromide cation. And when we are doing a reaction, we do not have just one molecule of each. Now you created a ketone. There are plenty of other methyl magnesium bromide Grignard reagent in our reaction mixture. So we know ketones react with the Grignard reagent. A second addition of the Grignard reagent occurs. Added to the carbon, and then pi bond opened up. Same thing happened that we already know. Now added two methyl groups. So the intermediate would be oxygen alkoxide ion with the magnesium bromide. And once all of these happen, you add acid. So then this can get protonated to give you alcohol, tertiary alcohol. Okay, and when you add acid, the methoxide ion also grab a proton from the acid, become methanol, and then magnesium bromide. Okay. So remember, when you have an ester, you add with a Grignard reagent, you will be adding two of the alkyl groups from the Grignard reagent, and then the alcohol. Okay, you would be end up getting a tertiary alcohol. Acyl chloride react with Grignard reagents and organocuprates. Now the acyl chloride also acts similar to the ester because this is a good leaving group, just like the methoxy group. Okay, so adding to ethyl magnesium bromide, similar to the mechanism that we had shown in the previous slide, carbon attack the carbonyl carbon, pi bond opens up, reform it, and then it would leave chloride and forms the intermediate RCO CH2 CH3 with one ethyl magnesium bromide. So the second ethyl magnesium bromide react with this ketone to give you the tertiary alcohol. So the acyl chloride and ester react similar together. Okay, they're working. They both react similarly with the Grignard reagent. Okay, adding two alkyl groups from the Grignard reagent. Also, acyl chloride can react with cuprates. Remember, we learned the cuprates in the previous section, previous chapter. So this is organic cuprate. So this can act as a carbon ion. Copper is positive, a metal. So it goes and attack to this carbon and it leaves this part. So you get a ketone. So an acyl chloride, if you want to stop at the ketone, the reagent that we should use is the cuprate. But if you want to get an alcohol, tertiary alcohol, then we use the ethyl magnesium bromide. Okay. So from the same starting material, we can get two different products based on the reagent we use. Okay, let's look at an example. How can 3-hexanol, it's not hexanol, it should be hexanone. Okay. This need to be, edit the text. Hexanone, N-O-N-E. How can 3-hexanone ketone be synthesized from 1-propanol? Okay, now let's see a small synthesis problem here. So this is 3-hexanone, 1, 2, 3, 4, 5, 6. So name of this compound is 3-hexanone. And you are asking how can you prepare it from 1-propanol. Normally in organic chemistry, when you are given a target molecule, we go back and backwards and see what are the needed pieces of molecules that we need in order for this reaction to go forward. We call that as retrosynthetic analysis, working backwards. So you have this one, and what we want to start it from propanol. Then we can think, okay, so you started with the ketone. How about we try to do it with a Grignard reagent? So then we know from a Grignard reagent, you can make an alcohol. So backwards, thinking backwards, so the ketone can be formed from an alcohol. Okay, and we know if you have an alcohol, you can oxidize alcohol to give you a ketone. We know that part. And then how can we get this alcohol? Because we have to find the pathway forward reaction starting from propanol. So we have to break it down until we go to propanol. And then what you're going to do is we're going to see, now this one has 1, 2, 3, 4, 5, 6 carbons. Now propanol is 3 carbons. If you break the bond here, meaning we can combine this carbon, let's say 1 and 2, using a Grignard reagent reacting with an aldehyde, and that aldehyde could be a 3 carbon long 1, 2, 3 propanaldehyde. Okay, if you react propanaldehyde with Grignard reagent that has 1, 2, 3 carbons like this, 1, 2, 3 carbons magnesium bromide reacting with propanaldehyde, meaning this carbon is going to form a bond here, open up, and then you form this alcohol. Now we found these two are going to give you this. But that's not the starting material we want. We want to get to the propanol. Now this is propanaldehyde. Propanaldehyde can be formed from propanol because propanol is the alcohol and we can oxidize alcohol to get aldehyde. And this is propane magnesium bromide, and we need to again make this one from propanol. Okay. Magnesium bromide Grignard reagent is formed between the propane and bromide, propyl bromide. Propyl bromide also can be formed from propanol by adding a bromide. So basically what we are looking at, starting with this, we can create the Grignard reagent as well as the aldehyde, and then when you mix together, you form the alcohol. Then oxidizing, you can get the ketone. So we were thinking backwards. Now we're going to see how can we go forward with the designed path. So you start with 1, 2, 3 propanol. To convert to bromide, you can add PBr3 and pyridine. Phosphorus tribromide and pyridine will give us propane bromide. And then adding magnesium and ether, we can create the propyl magnesium bromide. So we've got to one ingredient we want to make the this alcohol. And from this side, we also want to get an aldehyde. So the alcohol, you use the oxidizing agent, sodium hypochlorite and acetic acid. That would stop at aldehyde when you conduct the reaction at lower temperature, 0 degrees. Okay, aldehyde. Now we have an aldehyde and alkyl magnesium bromide. Now when you mix these two together in the presence of ether solvent, alkyl group attacks over here carbon. You know the mechanism now. This group goes and attack here and form the alkoxide anion. So the propyl group would add to the carbon. Now we have combined the two carbons, and now we have 6 carbons in our chain. 1, 2, 3, 4, 5, 6. We are one more step away from getting to the desired product. Again, you can oxidize this one, the alcohol, sodium hypochlorite and acetic acid. Under low temperature, alcohol can convert to ketone. So we converted, or we synthesized 3-hexanone from 1 propanol. Okay, so that is how we normally do a synthesis, and we utilize the Grignard reagent for this synthesis. Okay, let's stop this section here.